Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Cubesats, revolutionizing space exploration one tiny satellite at a time. The development of Cubesats represents a significant shift in the landscape of space exploration, allowing more accessible and cost-effective missions. These small satellites, measuring as little as 10 centimeters per side and weighing around a kilogram, were initially conceptualized as educational tools but have since evolved into essential components of both governmental and commercial space programs. Their rise in popularity stems from their compact size, which makes them relatively inexpensive to design, build, and launch. As a result, Cubesats have opened new opportunities for universities, private companies, and even developing nations to participate in space missions that would have been prohibitively expensive just a few decades ago. The increasing reliance on these tiny spacecraft has fostered a dynamic and innovative ecosystem of engineers, scientists, and entrepreneurs who are pushing the boundaries of what can be achieved in orbit and beyond. In the late 1990s, Cubesats were developed by professors Jordi Puigsuari from California Polytechnic State University and Bob Twiggs from Stanford University. They sought to provide their students with practical experience in designing and launching satellites. The simplicity and standardization of Cubesat components allowed students to build functioning spacecraft at a fraction of the cost and time it took to develop traditional satellites. The primary innovation behind Cubesats was their modular design. A single unit, or 1U Cubesat, measures 10 by 10 by 10 centimeters, with additional units, such as 2U or 3U Cubesats, stacked to increase capacity. This standardized sizing enabled the development of Cubesat-compatible hardware and launch systems, leading to a burgeoning industry that rapidly adopted the technology. The first Cubesat was launched in 2003, and since then, thousands have been sent into space, with uses ranging from Earth observation to scientific experiments and communications. Early on, Cubesats faced skepticism from the aerospace community, which was accustomed to large, expensive satellites with well-proven capabilities. The notion that something as small and cheap as a Cubesat could perform meaningful scientific work was met with doubts. However, the increasing miniaturization of electronics and improvements in materials quickly led to advancements that made Cubesats capable of sophisticated tasks. Today, Cubesats are used in various applications, including monitoring climate change, testing new technologies, and even exploring other planets. Their impact on the space industry has been profound, allowing a diverse array of participants to engage in space activities that were once the exclusive domain of large space agencies and defense contractors. One of the key advantages of Cubesats is their ability to be launched as secondary payloads on larger missions. Traditional satellites are expensive to launch because they require dedicated rockets, but Cubesats can hitch a ride with larger satellites, significantly reducing launch costs. As space agencies and private companies began to recognize the value of Cubesats, dedicated deployment mechanisms were developed, such as the Poly-Pico Satellite Orbital Deployer, PPOD, which allows multiple Cubesats to be released from a single rocket. This innovation drastically reduced the cost of accessing space, democratizing space exploration in the process. Universities, startups, and even high school teams could now design and launch their own satellites, contributing to a wave of innovation in the field. Cubesats have proven especially valuable in Earth observation, where they can be deployed in constellations to provide near real-time monitoring of the planet. This capability has been particularly useful for tracking environmental changes, such as deforestation, urbanization, and the movement of glaciers. Private companies have seized on this opportunity, with firms like Planet Labs using CubeSat constellations to capture daily images of the entire Earth. These images are used in applications ranging from agriculture to disaster response, offering an unprecedented level of detail and timeliness. The small size of CubeSats allows for large numbers of them to be deployed at once, creating a network of satellites that can cover vast areas with frequent updates. This is a stark contrast to the traditional approach of using a few large, expensive satellites to gather data, which may only provide sporadic coverage. The adaptability of CubeSats also extends to scientific research, where they are used for experiments in a variety of disciplines. NASA, for example, has used CubeSats to test new propulsion systems, study the behavior of fluids in microgravity, and investigate space weather phenomena like solar radiation. One of the more ambitious uses of CubeSats came during NASA's InSight mission to Mars. Alongside the main lander, NASA sent two CubeSats, named MarsCO-A and MarsCO-B, collectively known as the Mars Cube 1 mission. These CubeSats relayed communications from InSight as it descended to the Martian surface, demonstrating that small spacecraft could play a supporting role in interplanetary missions. The success of MARCO paved the way for future deep space missions involving CubeSats, proving that they could operate far beyond Earth's orbit. Despite their advantages, CubeSats are not without challenges. Their small size limits the amount of power they can generate, the instruments they can carry, and the volume available for propulsion systems. As a result, CubeSats are often limited to low Earth orbit, LEO, where they can complete their missions without the need for complex propulsion. However, innovations in miniaturized propulsion systems are beginning to extend the capabilities of CubeSats, enabling them to reach higher orbits or even venture into deep space. Another challenge is the relatively short lifespan of CubeSats, which typically ranges from a few months to a few years. This is due to their limited power supply, exposure to radiation, and the harsh conditions of space. However, advancements in materials and design are helping to extend the operational life of CubeSats, making them even more attractive for long-term missions. The rise of CubeSats has also raised concerns about space debris. Given the large number of CubeSats being launched, there's growing worry about the potential for collisions and the creation of debris that could pose a hazard to other spacecraft. Space agencies and companies are working on solutions to mitigate this risk, such as designing CubeSats that can deorbit themselves at the end of their missions or creating systems to track and avoid potential collisions. Additionally, regulatory frameworks are being developed to ensure that CubeSat operators follow best practices for reducing the risk of space debris. The commercial potential of CubeSats is vast, and private companies are increasingly investing in their development and deployment. Startups specializing in CubeSat technologies have attracted significant funding from venture capitalists, while established aerospace firms have incorporated CubeSats into their business models. For instance, SpaceX has launched Cubesats as part of its rideshare program, which allows small satellite operators to share the cost of launching on its Falcon 9 rockets. This has further driven down the cost of accessing space, spurring even more innovation in CubeSat applications. Beyond Earth observation and scientific research, CubeSats are also being used for communications, particularly in the development of small satellite constellations designed to provide global internet coverage. Companies like SpaceX, Amazon, and OneWeb are deploying thousands of small satellites, including CubeSats, to create a global network that will deliver high-speed internet to remote and underserved areas. This initiative has the potential to bridge the digital divide and provide internet access to billions of people worldwide. In addition to their commercial applications, CubeSats are being used in educational programs to inspire the next generation of engineers and scientists. Universities around the world have incorporated CubeSat development into their curricula, giving students hands-on experience in designing, building, and testing satellites. These programs not only provide valuable skills for students but also contribute to the growing body of knowledge about CubeSat technologies. Many university-built CubeSats have been launched into space, conducting experiments and gathering data that further our understanding of space and satellite technology. The future of CubeSats is likely to be shaped by ongoing advances in technology. As electronics and materials continue to shrink in size and increase in efficiency, CubeSats will become even more capable, performing tasks that were once the domain of much larger spacecraft. The development of advanced propulsion systems, such as electric propulsion and solar sails, will allow CubeSats to explore more distant destinations, including the Moon, Mars, and beyond. CubeSats may also play a role in future space exploration missions, acting as scouts or communication relays for larger spacecraft. The potential of CubeSats in interplanetary exploration is particularly exciting. NASA's Artemis program, which aims to return humans to the Moon, includes plans to deploy CubeSats to study the lunar environment and support the mission. These small satellites could map the surface, study the Moon's radiation environment, or even search for water ice in permanently shadowed regions. As humanity prepares to explore Mars and other destinations, CubeSats will likely play a crucial role in these efforts, providing low-cost, flexible platforms for gathering data and testing new technologies. In conclusion, CubeSats have revolutionized space exploration by making it more accessible, affordable, and innovative. What began as an educational tool has grown into a vital part of the space industry, with applications ranging from Earth observation to deep space exploration. As technology continues to advance, CubeSats will become even more capable, opening up new possibilities for scientific discovery, commercial ventures, and human exploration. Their impact on the space industry is undeniable, and their role in shaping the future of space exploration will only continue to grow.